Dear students, today we will discuss on chopper fed separately excited DC motor drive. In the previous class, we have discussed on the application of dual converters for speed and torque control of DC motor called as dual converter fed separately excited DC motor drive. We have solved numerical problems and we are able to determine the firing angle, speed, back EMF in case of dual converter fed DC motor drive. Today we will see on the chopper fed separately excited DC motor drive, and here by the end of the session you should be able to determine the duty ratio, which may be delta, K or D, anything, speed omega m or n, back EMF EA or EB, and power that is delivered by the motor uh, to the load for a chopper fed DC motor drive. So this is the last topic in this unit. We'll see this today. So why do we go for choppers when rectifiers are available for the speed control of the motor? The advantage with the choppers is that the choppers have high efficiency, flexibility in control, lightweight, small size, quick response, and regeneration down to very low speeds. This is possible because in case of rectifiers, we are having AC to DC conversion, but here DC to DC conversion, the choppers are operated at a high frequency. This reduces the losses and hence the efficiency is more. The chopper circuit is light in weight because of operation at high frequency. The inductance used is of small size. The total size of the circuit or the converter is also small. Quick response because the value of inductance that is added externally is very less as compared to inductance that is added in the rectifier controlled drives. So chopper controlled DC drives have found applications in servo motors and traction applications. In traction applications, we can use this in forklift trucks, trolleys, and in 1500 volts DC traction to replace resistance controllers. So there are many advantages. The main is that lightweight and quick response. Okay. Then in servo applications, separately excited DC motors are the permanent magnet field DC motors. That is what are called as PMDC motors. Permanent magnet DC motors are used because of the flexible and control characteristics. So these advantages of chopper fed DC drives are again discussed in terms of frequency of operation. If you take a chopper can operate at very high frequency. For example, if the choppers are designed with thyristors, what is a chopper circuit? If I have a chopper circuit, it is fed with DC and output is also DC. So, but what is here is the input DC is constant, but output DC is a variable one. So to get this one, we have to use the switches. We have to use the switches. So that becomes the chopper circuit. This switch can be a thyristor. If a converter grade thyristor is used, chopper can be operated up to 300 Hz. If inverter grade thyristors are used, we can operate the chopper up to 600 Hz. If, for example, this thyristor based choppers, if they are operated with low output voltage, then we can increase the frequency up to about 800 Hz. On the other hand, BJTs, power transistors, if they are employed, power BJT, if they are employed, we can operate up to 2.5 kilohertz. This is the major advantage. And for low and medium power applications, MOSFETs can be employed as the switches. MOSFETs can be employed as the switches, and they can be used up to 200 kilohertz. See the range of frequency, we can operate up to 200 kilohertz. But if, for example, the DC drive is designed with a controlled rectifier, instead of chopper, we use a controlled rectifier, then the lowest frequency that you can operate is 100 hertz, and the maximum frequency that you can operate is 300 hertz. Now, this is because if the input supply voltage frequency is 50 hertz, is 50 hertz. In case of full wave rectifier, we are getting the output waveform like this, and hence the time period is become half, and the output frequency has doubled that of supply frequency. So that becomes 100 hertz. In case of three-phase full wave rectifier, we are having six pulses in one cycle, and hence the output frequency will be six times the input frequency, that is 300 hertz. So maximum we can operate at 300 hertz. But on the other way, if we employ MOSFETs, we can operate up to about 200 kilohertz. That is the advantage. There are various types of choppers, and they can be classified based on the input output voltages. What is the level of input output voltage? We can classify the choppers as step down choppers, step up chopper. In case of step down chopper, output voltage, let us say V0, is less than the supply voltage, let us say Vs. In case of step up choppers, output voltage V0 is greater than supply voltage Vs. So this is what the main thing. Based on the voltage magnitude or voltage levels, we can classify the choppers as step down and step up choppers. Similarly, according to the direction of voltage and current, that is based on voltage and current polarity, we can classify them as class A, B, C, D, and E. See, in case of class A, it is that voltage and current both are positive. In case of class B, voltage is positive, current is negative. In case of class C, voltage is positive, current can be positive or negative. So it operates in two quadrants. In case of class D, voltage is positive or negative, but current is always positive. In case of class E, we can have both the polarities of voltage and current, and hence it is four quadrant operation. So based on the quadrants of operation also, we can classify the choppers as one quadrant chopper, two quadrants chopper, and four quadrant chopper. So one quadrant choppers are what? Class A and B. Two quadrants choppers are what? Class C and D. And there is class E, which is a four quadrant chopper. So let us now come to the DC drive, how choppers can be employed for motor control. So let us say I want to operate the DC motor in forward motoring operation. Then in that case, if I see the voltages and currents, both are positive, and the motor should operate in the first quadrant. So the chopper that is suitable for this is shown in the figure. So here, when the chopper is on, when this switch is on, when the chopper switch is on, there is a connection here, and hence supply is connected to the load. The inductor current starts to rise. The inductor current starts to rise. And when the chopper is off, supply is disconnected from the load. Now, whatever the energy that is stored in the inductor and the back EMF will be able to supply current through this freewheeling diode. So what is happening is you are connecting and disconnecting the supply, and during this time the current through the inductor is rising and decreasing like this. So the average voltage and current directions, if you see, they are always positive at the load terminals, and hence the motor operates in the motoring operation. The motor is in motoring operation. So if you see the waveforms, when the chopper is on, when the supply is connected to the load, the output voltage, that is nothing but armature voltage, output voltage of the chopper, or armature voltage of the motor, it will become EDC, that is supply voltage. You can see here. So when the chopper is on, this VDC is directly connected to this armature terminal of the motor, including this external inductance. So that at this point, this E naught will become EDC. Okay, E naught will become EDC. That is this one. When the chopper is off, supply is disconnected and voltage drops to zero. But because of high inductance, current does not change instantaneously. When supply is connected, current changes or increases like this. So current increases like this, and when the chopper is off, current decreases like this. So there is increase and decrease of current. Okay. So if you now take the equations, performance equations here, when the chopper is on during the period 0 to t on, I have the KVL equation like this. EDC, that is this one, EDC EDC is equal to L into d I naught by dt plus RA. Here RA represents the armature resistance, and let us say EB is the back EMF. RA into I naught plus EB. Similarly, when the chopper is off, it is disconnected. Now there is circulating current here only. So we have RA into I naught plus L into d I naught by dt plus EB is equal to 0. The diode terminal short circuits the armature terminals. Okay. And the average output voltage E naught. So based on the waveform, we can see here. Now, if I integrate this waveform from 0 to t on EDC into t, and take the average for one cycle, I get the equation E naught. I get the output voltage equation E naught is equal to the supply voltage EDC into T on divided by T. Okay, EDC into T on is the area divided by T, that gives the average value of the voltage. And this ratio T on by T is called as delta, and that is called as the duty ratio or duty cycle of the chopper. And this, what is the, if you see the waveform here, if you see the waveform here, this T on can vary from where to where, 0 to maximum T. So therefore delta, which is T on by T, varies from 0 to 1. So during that time, the current now will be given by delta EDC minus E by RA. How do we get this equation? This is nothing but IA is equal to the supply voltage. This is the armature voltage VA minus back EMF divided by RA. Okay, so that is equal to VA or V naught. The average output voltage is nothing but what, delta EDC minus the back EMF divided by A. So this is the equation. So the speed similarly will get omega m is equal to EDC into delta by KE5 minus RE into T by KE5 whole square. So this is the machine speed equation. Similarly, I can operate the motor in regenerative braking mode by using chopper. So in that case, the chopper connection should be like this. The chopper switch is connected in shunt with the armature terminals, and diode is connected in the reverse direction here, because during regenerative mode, current is supplied from load to the source, and hence current or power flow should be in this direction. That is done by using a diode. So here, what is happening is the voltage is positive plus minus. Okay, voltage is positive and the current is negative. So therefore, the motor operates in the second quadrant. The motor operates in second quadrant, and this is the regenerative braking mode of operation. So now in this case, what is happening? See the circuit when the chopper is on. When the chopper is on, okay, there is a connection here. Now the armature is short circuited, and hence the energy stored in the inductor will be supplying power to the load. And when the chopper is off, the energy is supplied back to the source. Okay. So what is happening here? So when the chopper is off, the inductor current is changing like this. Now we are having negative currents, and when the chopper is on, okay, when the chopper is on, we are giving gate pulse here. When the chopper is on, output voltage is zero, and the current decreases like this. So this is how the current waveform goes, and the average current will be somewhere here. Average current will be somewhere. So the again the equations are what delta is T on by T, and average output voltage is EDC divided by 1 minus delta. IA is nothing but E minus EDC by 1 minus delta. See here EB, this is back EMF. Back EMF minus average output voltage, because now the current direction is reversed. So and the torque is minus K into IA and omega M is same. Okay. The advantage with the chopper is normally we want to operate the DC motor in motoring and the regenerative braking mode. I can make use of one single circuit to operate in first quadrant and second quadrant. See the connection here. In this case, now the chopper CH1 and D1 will be similar to that of the step down chopper for first quadrant operation, and chopper 2 and D2 are similar to the switches for operation in second quadrant operation. So here delta is a T on by T, and again the EMF current and speed equations are given. So if you see the waveforms, it will be like this. You can see here when the gate pulses are given IG, when the gate pulses are given, when IG is on, chopper is on, IG1, IG2. So here the CH1 is on. When CH1 is on, output voltage will appear here. And here when CH2 is on, output voltage will be zero. So this is how you can see here. And the current is both negative and also positive. Instantaneous current is both negative and positive. And in this case, if you can see here, this is negative area of the current. This is the positive area of the current. Positive area is more, and hence the average current is positive. Average current is positive means now the motor is operating in motoring operation. If I gradually decrease this T on and increase the T off, then what happens? Positive portion will be less and negative portion will be more. In that case, the average current will be negative, indicating that the motor is operating in regenerative braking mode. Yeah, we can also have this connection which we have used for regenerative mode for dynamic braking. In case of dynamic braking, what we do? We connect an external resistor to the motor. So instead of supply voltage, if we connect an external resistance or braking resistance, then the motor operates in dynamic braking mode. So you can see here the waveforms looks same, but the thing is power is now supplied to the resistor. So the energy, if I calculate what is the energy consumed by the braking resistance, energy consumed by braking resistance is I naught square RB into T minus T on, because it absorbs power during T off, during off period. Here the current and voltage both are there. During the T on period, current is existing, voltage is zero, so power absorbed will be zero, voltage into current. But during T off, power is absorbed by the resistor, and that power absorbed is nothing but E average by T, and that is equal to I naught square RB into 1 minus delta. So the effective value of braking resistance RBE is nothing but RB into 1 minus delta, RB into 1 minus delta. Yeah. Let's see a problem here. A 230 volts, 960 RPM and 200 amperes separately excited DC motor has an armature resistance of 0.02 ohms. So motor ratings are given. Then the motor is fed from a chopper which provides both motoring and braking operations. The source has a value of 230 volts. Assuming continuous conduction, what we have to find? We have to find duty ratio, that is delta, for what? Motoring operation, and rated torque and speed is 350 rpm. So here these are the rated conditions and these are the new conditions. So let us first what we shall do is First calculate what is the back EMF under rated conditions, and the rated values back EMF is 226 volts. Now for new speed, now calculate what is the back EMF. We have the equation E2 by E1 is equal to N2 by N1. With that we get the new back EMF as 82.4 volts. As it is given that the torque is the rated torque, current also remains at the rated current of 200 amperes. Now the armature voltage or motor terminal voltage VA2 is E2 plus I2 IA2 into RA, and from that you get the armature voltage as 86.4 volts. Armature voltage is 86.4 volts, and hence the duty ratio will be equal to output voltage by input voltage. Output voltage is armature voltage, input voltage is supply voltage, and that comes to 86.4 by 230, that is 0.376. Okay, there are no units for this, it is the ratio of voltages. So similarly, we can find out what will be the back EMF under new conditions. You can please go through this problem. If there are any doubts, you can please interact. So today we have seen the equations for average output voltage of class A and B choppers, and also for class C chopper, quadrants of operation with motoring and braking operations we have seen. Then determine the duty cycle speed, back EMF, and of chopper fed separately excited DC motor. Okay, so dear students, by now you should be able to solve some numerical problems related to this. So for this, you please remember the average output voltage equation, that is delta times EDC for step down or class A chopper, and average output voltage is EDC divided by 1 minus delta in case of class B choppers. Yeah. So the lecture level numerical questions are also shared, and for further understanding that, you can please refer GK Dubey chapter 5, 5.18 and 5.19 section, and examples 5.19 and 5.20. There are a good number of exercise problems given in GK Dubey. You can try to solve these three problems.